Welcome to today's paper reading. Today's paper is titled, Long-Form Factuality in Large Language Models. This paper was published on the AR14 preprint by Jerry Wei and colleagues from Google DeepMind. Large language models, LLMs, frequently produce content containing factual inaccuracies when responding to fact-seeking prompts on open-ended topics. To assess a model's long-form factuality in open domains, the authors utilized GPT-4 to create LongFact, a comprehensive prompt set consisting of thousands of questions across 38 diverse topics. They introduced the Search-Augmented Factuality Evaluator, SAFE, a method that employs an LLM to decompose a long-form response into individual facts and evaluate their accuracy through a multi-step reasoning process involving Google search queries. SAFE aims to extend the F1 score as a metric for long-form factuality by balancing the precision of supported facts with recall based on a user-preferred response length. Empirical results show that SAFE can outperform crowdsourced human annotators, agreeing with them 72% of the time and winning 76% of the time in disagreement cases, while being over 20 times cheaper. The authors also benchmarked 13 language models on LongFact, finding that larger models generally exhibit better long-form factuality. Figure 1 illustrates our automatic factuality evaluator, SAFE, which employs a large language model to assess the factuality of long-form responses to given prompts. The evaluation process involves using Google search to verify the accuracy of individual facts within the response. Empirical results show that SAFE not only matches but also surpasses the performance of human annotators, achieving a 72% agreement rate with human annotations. Additionally, SAFE is more than 20 times cheaper than human annotators, making it a highly efficient and effective tool for factuality evaluation. The introduction highlights the significant improvements in large language models, LLMs, over recent years, as evidenced by studies from 2020 to 2023. Despite these advancements, LLMs still face challenges with reliability, particularly in responding to in-depth factual questions. Factual errors, where model claims contradict established knowledge, are a recurring issue. These errors can manifest in incorrect information about dates, statistics, and other factual details, undermining the model's credibility. The research aims to address these inaccuracies, thereby enhancing the reliability of LLMs and contributing to the advancement of the field. The authors introduce LongFact, a new prompt set generated using GPT-4, consisting of 2,280 fact-seeking prompts across 38 topics. This set is designed to evaluate long-form factuality in large language models. Additionally, they propose SAFE, a method that uses an LLM agent to automatically evaluate the factuality of model responses by decomposing them into individual facts and checking these against search results. To quantify long-form factuality, the authors introduced the F1 at K metric, which measures both precision and recall, with recall adjusted by a hyperparameter K that estimates the ideal number of facts in a response. Figure 2 provides an overview of LongFact, a comprehensive prompt set designed to evaluate a model's ability to generate factually accurate long-form responses. On the left, the figure outlines the 38 distinct topics that LongFact covers, which are categorized into 4 main supercategories: STEM, social sciences, humanities, and other. These topics are selected to ensure a wide-ranging and thorough assessment of factuality across various domains. On the right, the figure contrasts LongFact with existing factuality datasets, highlighting 2 key features. First, LongFact focuses on long-form responses rather than short answers, which allows for a more detailed and nuanced evaluation of a model's factual accuracy. Second, LongFact covers a significantly broader range of topics, ensuring that the evaluation is comprehensive and inclusive of diverse subject areas. This dual focus on length and breadth makes LongFact a robust tool for assessing the factuality of long-form responses in large language models. The primary challenge in evaluating long-form factuality is the need for a reliable method to assess model responses. Existing methods like BLERT, Rouge, and prompting language models are effective for short answer responses but are inadequate for long-form ones. This is because long-form responses require comprehensive and non-redundant coverage of facts, which is difficult to achieve with predetermined answers. Instead, the authors propose two key insights: evaluating responses at the granularity of individual facts, and using Google search for dynamic reference answers. These insights form the basis of the Search-Augmented Factuality Evaluator, SAFE. SAFE uses a language model to split long-form responses into individual facts, determine their relevance, and iteratively issue Google search queries to evaluate the support for each fact. This multi-step process ensures a thorough evaluation of long-form responses. Figure 3 illustrates how SAFE accurately rates factual claims that require multi-step evaluation. It leverages a language model to iteratively issue Google search queries and reason with the obtained search results. This process ensures that each factual claim is thoroughly evaluated, contributing to the overall accuracy of the factuality ratings provided by SAFE. The study demonstrates that large language models, LLMs, can outperform human annotators in factuality tasks. LLMs have shown superhuman performance in reasoning benchmarks and higher factuality in summarization tasks. In a comparison of 16,011 individual facts, SAFE annotations agreed with human annotations 72% of the time, indicating human-level performance. Additionally, SAFE is significantly more cost-effective, costing 19 cents per model response compared to $4 per human response, making it over 20 times cheaper. In cases where SAFE and human annotations disagreed, SAFE was correct 76% of the time, while humans were correct only 19%, resulting in a 4-to-1 win ratio for SAFE. These findings suggest that LLMs can serve as scalable and superior alternatives to human annotators. Figure 4 illustrates the agreement between SAFE annotations and human annotations on a dataset of 16,011 individual facts. The results show that SAFE agrees with human annotations 72% of the time, indicating that SAFE achieves human-level performance on a majority of these facts. This figure is crucial for understanding the reliability and accuracy of SAFE in comparison to human raters, providing a quantitative basis for its potential to replace human annotators in long-form factuality evaluations. Figure 5 illustrates the superior performance of SAFE over human annotators in terms of accuracy and cost efficiency. On the left, it shows that SAFE correctly annotated 76% of the disagreed facts compared to only 19% for humans. On the right, it highlights the cost difference, where SAFE costs 19 cents per model response, significantly cheaper than the $4 cost for human annotations. This results in a 4-to-1 win ratio in favor of SAFE, demonstrating its potential as a scalable and cost-effective autorator. In long-form factuality, precision measures the percentage of supported facts among all facts in a response, while recall measures the percentage of provided facts among all relevant facts. However, measuring recall is challenging due to the difficulty in defining a definite set of facts that should be included. To address this, the F1@K metric combines factual precision and recall, bounded between 0 and 1, where a higher score indicates a more factual response. For a response to achieve a full score of 1, it must not contain unsupported facts and must have at least K supported facts. This metric allows for standardized and quantifiable comparisons between language models. The performance of various models, as measured by F1@K, shows a relatively stable ranking at sufficiently large K values, facilitating clear comparisons. Figure 6 illustrates the long-form factuality performance of 13 large language models from 4 model families: Gemini, GPT, Claude, and Palm 2. The models are sorted by their F1@K scores in descending order. The F1@K metric was calculated using two values of K, 64, which is the median number of facts in model responses, and 178, which is the maximum number of facts. This evaluation was conducted using SAFE on responses to 250 random prompts from LongFact objects. The stability of model rankings at larger K values is discussed in Appendix E.3, and raw metrics are detailed in Table 2. In this section, the authors benchmark 13 large language models from 4 different families: Gemini, GPT, Claude, and Palm 2. They use a random subset of 250 prompts, each with a fixed postamble to increase difficulty. The evaluation includes raw metrics such as the number of supported, not supported, and irrelevant facts, as well as aggregated metrics like precision, recall at 64 and 178, and F1 scores at these levels. The results show that larger models generally achieve better long-form factuality, with models like GPT-4 Turbo, Gemini Ultra, and Palm 2 Lite RLHF performing the best. This suggests that within each model family, the larger models tend to be more factual. Table 1 lists the models benchmarked in this paper, categorized by their respective model families. The Gemini models include Gemini Ultra and Gemini Pro. The GPT models include GPT-4 Turbo, GPT-4, and GPT-3.5 Turbo. The Claude models include Claude 3 Opus, Claude 3 Sonnet, Claude 3 Haiku, Claude 2.1, Claude 2.0, and Claude Instant. The Palm 2 models include Palm 2 Lite RLHF and Palm 2 Lite. These models were evaluated on the same random subset of 250 prompts to assess their long-form factuality performance. Table 2 presents the comprehensive benchmarking results of 13 large language models across 4 model families, Gemini, GPT, Claude, and Palm 2, on the same set of 250 random prompts from LongFact objects. The metrics are averaged over all prompts and include raw metrics such as the number of supported, S, not supported, NS, and irrelevant, I, facts, as well as aggregated metrics like precision, PREC, recall, RK, and F1 at K equals 64 and K equals 178. These metrics are crucial for understanding the long-form factuality performance of each model, with K values chosen to reflect the median and maximum number of facts among all model responses. In the realm of factuality benchmarks, several recent studies have introduced various benchmarks such as FELM, FreshQA, and HaloEval, which primarily test a model's knowledge of factoids. Adversarial benchmarks like TruthfulQA and HaloQA are designed to test whether a language model will generate false factoids. Long-form factuality benchmarks, such as those proposed by Min et al., require models to generate biographies evaluated against Wikipedia articles. When evaluating factuality, short ground truth answers can be assessed using fine-tuned language models, while long-form responses are more challenging due to their broader range of factual claims. Tools like FXScore and RAGAs leverage external knowledge sources and consistency checks. Quantifying long-form factuality involves measuring both precision and recall, which is challenging. Metrics like FXScore focus on precision, while F1 at K measures both precision and recall without preset ground truth answers. The effectiveness of LongFact and SAFE is heavily dependent on the capabilities of the used language models, LLMs. These models must excel in instruction following, reasoning, and creativity to generate high-quality prompts and responses. For instance, a model that struggles with following instructions might produce prompts that deviate from the intended topic or fail to elicit long-form responses. In the case of SAFE, a weaker model could decompose responses inaccurately, exhibit poor relevance determination, propose unrelated search queries, or fail to properly assess search results support. Despite these challenges, the current configuration of SAFE uses GPT 3.5 Turbo, which offers a balance of performance and cost efficiency. However, there is potential for future work to explore fine-tuning cost-effective models to enhance performance. Additionally, SAFE's reliance on Google Search as a knowledge source introduces limitations, particularly in corner cases and expert domains where search results may be insufficient. To address this, the system labels facts based on Google Search support rather than global factuality. Finally, the F1 at K metric, while robust, assumes no repeated facts, which could theoretically be exploited. This limitation could be mitigated by additional metrics or pre-processing steps to remove duplicates, though this remains a topic for future research. In this paper, the authors examined how to benchmark long-form factuality in large language models. They used GPT-4 to generate LongFact, a dataset of 2,280 prompts across 38 topics. The SAFE method was proposed to evaluate long-form factuality by splitting responses into individual facts and checking their relevance and accuracy. Empirical results showed that SAFE agreed with human annotators 72% of the time and was 20 times cheaper. Future research could focus on improving model factuality through better training or tool use, enhancing safe, and developing methods to measure hallucination in long-form responses. Thank you for watching.